All right, so in today's class, as I said, we are going to be looking at set operations. So we are looking at set operations. So set operations allow us to combine or modify sets into new forms. So now these set operations that we're going to have, so we're going to learn them in this way. So we'll look at what the union of a set is, of two sets is, or many sets. What is the union? Then we'll look at the intersection. What do we mean by intersection of a set? Then we'll move on to complement of a set. Then from there, we'll look at the set difference. So now let us go in that way. So okay, so we have first the union of a set. So the union of a set of two sets. Now I'm saying the union of two sets A and B. So if we're to bring A and B set, we have a set A. Okay, suppose we have a set A and B. So A and B there denoted. So we're saying the union is going to be denoted in this way. If we're bringing A union B, it will be denoted in this way, where this symbol in between, this symbol which looks like a U here, like this, is for union. Then we're saying, is the set containing all elements that are in A or in B or in both? So the elements, so the union of this set, when I say A union B, it just means that these are elements that are either in A or they are in B or they are in what? They're in both sets. So by definition, A union B, as you can see here, A union B is such that it's a set of all X such that X is either a member of A or X is a member of what? Of B. So it's either in what? In the set A or it's in the set what? In the set B. Or it can be in what? In both of the sets. So now let us look at an example here. So the example is saying let A equal to, so you have the set A contains the numbers 1, 2, 3. Then the set B contains 3, 4, 5. Then they're saying A union B. So we're saying A union B just means that these are elements that are either in A or in what? In B or in what? In both. So it just means that we are bringing all the elements together. So I have the set A and the set what? The set B. It means that I'm bringing all the elements together. So I have 1, 2, 3. Here I have 3, 4, 5. So remember that when you are listing out sets, we have to make sure that it is definite, meaning that numbers should not what? Should not repeat. So where you have 3 here and 3 there, meaning you only write 3 once. So you write 1, 2, 3, 4, 5. So you've brought all the elements towards together, and that is what? The union of a what? Of a set. And if we are to use, now you look at notation as we go on, where we start looking at Venn diagrams. So you have a Venn diagram like this. And let's say I have a set A and what? And B here. So A and B, then of course I have a set E here. What this would mean is that if I say union A union B, it means that what? I am bringing everything to what? Together, like this here, everything together. Everything in A or in what? Or in B, they must come to what? They must come together. So the element X, which is an arbitrary point, we're saying is either in the set A or it's in the set what? In the set B. And of course, that which would mean that it's either what? If it's in A or in B, then it can be what? In both of the sets, is what we're saying. And for our example, as you can see our example, for this example here, so you have 1, 2, 3. So, and you have 2, 3, 5. So you see what is common here is 3. And usually what is common, you will sit in between there. And you look at it in the next part, which we are calling intersection. Then what remains, you put it in the part of the set that what that remains. So you have 1 and 2 remain here. Then the other one that remains here is what? Is 4 and 5. So this, bringing all these sets together, A and B, this is what? Is a union of what? Of the sets. But of course, even if the sets did not have anything in common and we say union, for example, say the 3 is not here. Let's say we do not have a 3 in both sets and we just have set A. Let's say set A is equal to 1, 2, like this. Then B is equal to, the set B is equal to 4 and 5. So if we were to write them, you would have your A and your B there. So you have A and B because they do not have anything in common. So you don't bring them together, or you don't form that intersection. So what then here, you put your elements 1, 2, then you put your other elements here 4 and what and 5. The union of these sets is you're bringing everything together now. So it means that here, everything in here like this and everything in there is going to be A union B. So when I list my A union B for that case, it has to be 1, 2, 4 and what and 5. So it just means that I'm bringing everything towards together. Right, so that's the concept of what, of union. So by definition, set of what, of OX, such that X is either in A or it's in the set what, in the set B. And you would see here the way we've written it. Now let us move on to a concept of intersection, because we've already brought it up here. So uh, we go on. So intersection is represented by this symbol here. Looks like an N, but written in a way that does not have that going out way, I would say. Yeah. So like this. Or the same symbol of union just upside down is what is the intersection, is what we're saying. Now, what is this intersection? So the intersection of two sets A and B. So intersection of a set A and B, denoted, of course, is written like this. A intersect B is written like this. Is the set containing all elements that are common. Keyword here is common. The keyword is common. Elements that are common in both sets, then those they will sit in the what, in the intersection. So what does that mean? By definition, we mean that it's a set of OX such that X has to be in A and X has to be in what, in B. The element must exist in both sets. It must be in A and it must be in B. And you can see for what, for our example here, we have A, the same example which we are what we're using. So we have A as 1, 2, 3. So that's our A, 1, 2, 3. Then you have your B. Your B is 3, 4, 5. 3, 4, 5. Then your intersection, remember, it has to mean that elements that are common in both sets. So you see, what is common here? So you see that there's a 3 here and there's a 3 here. So that 3 is in A and is in B. So meaning it's going to be what? In the intersection of what? Of those sets. And as we wrote it down in our Venn diagram, as we had written, so you have this A and B. So you have A and B. We are bringing them together because they already have an intersection that we know, which is what? Which is 3 from this question. So 3 will sit there, and of course the rest are going to sit here. You have your 1 and 2 and 4 and 5. So this in between part, this part here where I've shaded here, this is the intersection of what, of those sets, the element that is common in both sets. And of course this space that remains outside here where this set sit is what we call the universal set. Yeah, it's noted by E, or others would use U for universal set, of course. So E, or denoted by what, by E. All right, the next concept now we are to understand is complement. What do I mean when I say complement? So you see here saying the complement of a set, say A complement is written, so it's written as A complement like this, with a uh, with 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 this quote per se like that. So you have A, then the prime there like that. So this is the A complement. Or in other books, or you can write it as same as A, then you put a C there. You mean the same thing. You're just talking about the complement of what, of a set. Now, what is this complement of a set? So the complement of a set A. So the complement of a set A, denoted by, of course, as we said, denoted in this way or in this way, is the set of what, of elements in the universal what, in the universal set that are not in A. So what are we trying to say here? So first of all, the universal set, you must understand what it is. So the universal set denoted U, of course, we're saying U, or we can say what, E, capital E like this, is the set of all possible outcomes under consideration. So for example, if I say my set, let me have a set, um, I'll define A, and my A, let it be a set of, so there'll be 2, 4, then what? I'll say 6, just like this. Okay. But then I say my universal set U should be defined 2, 3, 6, of course, going up to infinity like that. So now the universal set now, the set of all possible outcomes, I want it in this case, as we have seen, is a set of what? Of even numbers. So the set of what? Of even numbers. The set of all possible outcomes are what? Are even numbers. And A is just the what? Is just a set that sits in what? In there. I would say it's a subset in what? It's a subset of that universal set. Because A, we see these 2, 4, and 6 are just even numbers. So because they're even numbers, they are going to be a subset of what? Of the universal set, which is a set of what? Of all even what? Even numbers. So the universal set is just a set containing all possible outcomes under consideration based on what we are looking at. Then the complement of the set now, A, complement of a set A, are just all elements that are what? That are not in the set A, but then they sit in the universal set. So the elements are not in A, but they sit in the what? In the universal set. For example, so by definition, we can write it as this: A complement is going to be equal to X, such that X is in what? The universal set, and X is not a member of what? Of A. Of course, you can write it as X, not a member of what? Of A. So X is not in A, but it's in the universal set. So now, meaning you always have to have a universal set for you to know the complement of what? Of that set. So if you have, let's say A, so we say, let's say our universal set is this here. Is a set of numbers from 1 to 5. Then the set A, which is a subset, of course, of the universal set, is a set containing the numbers 1 and 2. So A complement are those numbers that are what? That are not in the set A, but are in the universal set. They are not in A, but in the what? Universal set. So I see that is 3, that is what? 4, and that is 5. And that will make up my a complement. So to note is just to say that every element that is not in A but is in the universal set is going to be in the complement of what? Of the set A, or is going to be in A complement. Okay, so that is all about what? About complement. Now we look at this the last part, as we said, the difference now. So uh, set difference is written as A, I would say dash, you're saying dash or minus what? B, or you'd see other notation A, they put a slash like this, what? Slash B. This is how we denote the difference of two sets, A and what? A and B. So now, what does this mean? This is just a set containing all elements that are in A. So all elements that are in A, but they are not in what? They are not in B. Elements that are in A, but not in what? Not in B. So by definition, is a set of all X such that X is supposed to be in A, but X is what? Is not in B. This dash was supposed to cancel here to say A, not a member of what? Of B. Uh, and removing, of course, this line here. But A, not a member of B is what we're saying. So X has to be in A, but X is not in B. X is in A, but not in B. That's what we mean. So all possible elements, all elements that are contained in A, but are not contained in what? In B. That is the set difference. So here we have the set A and we have the set B. So A minus B, or the set difference of A and B, is going to be, so I check what elements are in A but not in B. There are elements that are what? That are contained in A but are not in what? In B. So I check which ones are not in B. Oh, here, okay. I see 3. Okay, 3 is in B. 4 is in B. Oh, which one is not there? Oh, it's actually 1 and what? And 2. 1 and 2 are not there. So these are the elements that are going to be in my A. The set difference of A and what? And B. That is the case where I start from A and B. Then what if I do the other way around? So A minus B, or the set difference between B and A. So it's all elements now that are in what? That are in B, but are not in A. So I check elements that are in, okay, 3. Is 3 in A? Okay, 3 is there in A. Is 4 in A? 4 is there in A. But it's 5 in A. 5 is not there. So meaning 5 is going to be what? 5 is going to be in my what? My difference there is going to be in my set difference. So this can also be thought of as to say, so if I say A minus B, what I'm just saying, this is going to be equal to A intersect B complement. A intersect what? B complement, which you'll see further on. Now, uh, you would see here. So the set A I already have, but B complement. So what is B complement? Now it would require me to have the universal set, of course. In this case, like I needed to have a universal what universal set defined. But in fact, I can define my universal set. Let me define my universal set. Say, okay, my universal set is 1, 2. I just bring all the elements together because let me just say so. 1, 2, 3, 4, 5, and let me even put 6, just like that. So let's say this is my universal set. Then now, I looking at the set difference of A and B could be looked as A intersect what B. So my A I already have. Let me look, what is my B complement? So B complement, remember complement, elements that are what? That are not in that in the set in the set. So in this case, we're saying B complement. So they are not in B, but they sit in the universal set. So not in this B here, but they'll be in the universal set. So what elements are those? So if I look, there's 1. It's not in B, but it's there in the universal set. There's 2. It's not in B, but it's there. Which one else? There's what? There's 6 there. So like this. So now I intersect them. So I'm intersecting. So my A is 1, 2, 3, and 4, like this. Then intersect this one here, which is 1, 2, and 6. Then intersect, we said elements that are just common, that are both in these both sets, like it's in this set and the other set. And what elements are those? So you look at this here, you see, oh, 1 is there, 1 is there, 2 is there, 2 is there. These are the what is common, and you get that 1 comma 1 comma 2, which is the same answer as what? As this one here. So the set difference could be looked at as A intersect B complement. Okay, so I don't know if we have any question thus far before we move on. Does anybody have any question? Are we together? Have we understood the set operations which we have before we see how they are applied elsewhere now? Okay, so there's no question. Now, let us move on to look at this. So this is we are looking at so the laws of algebra of what? Of sets. Of course, under the operations of the union and the what and the intersection, and all the other two operations we've looked at, which is the complement and the difference. So now, what are these? What are these laws of what? Of algebra? So first of all, you'd see here you have A union B. Of course, we'll prove some of them will not prove them. You can just take time and what and look at them. So you have A union B, for example. So this is a law to say every time I have A union B, what I'll get is just A. So A union B will give me A. How true is that? I can draw this actually in what? In a Venn diagram. If I have A, the set A and A, in fact, you can reason, set A and A are the same. So it means if I bring everything in A and everything in A, I still get A. So this is what this law is saying. The next one is intersection. If I have the set A and if I have the set A intersecting the set A like this, then the elements that are common in both sets, so elements that are common in A and elements common in A, they're common in both. So it just gives me A again. Then the next one is what we're calling the complement here, or the difference. So the difference, I mean, the set difference of A. So look at the set difference of A written like this there of A is just it could be further expressed as A minus what? Minus B, or in that other notation, as we said, which is the same. Remember what we built on. It's the same as saying A intersect A complement. So A intersect what? A complement. Now, this one, for this one, let me draw a Venn diagram like this. So if I have A here, this is my set A, and I have the inverse set here. So if I say the set A is this one, A complement everything that is not in A but is in the universal set. So my A complement is this one. This outside part here is my A what complement. So I may say this A complement. That's my A complement. And this is my A. Then they're telling you intersect these two side things. Do they have anything in common? As you can see, there's nothing in what in common. Because if there was something in common, would have shaded them the same parts. So let me just differentiate it to say, okay, this is my A, like this is my A, then that one is my what is my complement. If they were intersecting, then you would have either had lines crisscrossing each other or would have a common shaded part. But now they are even shaded in different white colors just for demonstration's sake to see. But this then would mean that, oh, my A intersect what? My A intersect A complement is just going to be an empty set. There'll be nothing there. Then you look at this. So the rule that follows here is just the rule that follows is commutativity. So commutativity just means, for example, we know addition is commutative. 3 plus 2 is the same as 2 plus 3. No matter what order I'm going to write them, the answer is going to be the same. And that is the same also with what? With multiplication. Multiplication is also commutative. Me writing 3 multiplied by 2, I mean 2 multiplied, yeah, I mean 3, 2 multiplied by 3 and 3 multiplied by 2, this here is just the same thing. They all give me 6. But with things like mm, things like subtraction, you see that it's going to be what? It's going to be different. 7 minus 5 is not equal to what? To 5 minus 7. This here gives you a 2. This here gives you a -2. So you see that there's that difference there. But commutativity, in this case, we're saying union and intersection are commutative, where if I have two sets, I'm doing the union of two sets, A and B. It's the same, even if I write B union A, I still get the same answer. If I'm doing A intersect B, intersection now, even if I write B intersection A, I still get the same answer. So this is the law of what? Commutativity. Commutativity. Commutativity, yeah, like this. So that is what you get. The next one here is the associative law. So the next law that follows is the associative law. So on the associative law, what we are saying is A union B, A union B union D is the same as saying A union what? Union B. I mean A union, then the union of what? Of A union what? Union B. So this just means that, okay, if I have the operator union, and then I'm uniting the two sets first, A union B, then uniting it with what? Or bringing every element in common, bring every element, I mean, not in common, but every element that is there, then since it's just union, I can then do to say, okay, I can do the last two first. To say I do B union what? Union D. I do this union first, then I come and do what? A union. Then I unite this set with what? With A. It's the same. Same with intersection is what we're saying. A intersect what? Intersect B. Intersect D is the same as A intersect. Then I intersect with what? With the intersect of B intersect D. So this is what we call the associative law. This is association, our associative law. Associative law. So this is what we call that. Then the next one is what we call the distributive law. So on the distributive law, it just means, you see here I have A union, then inside, now the sign has changed here. So A, here I have union, they have intersection. So distribution means, okay, I can distribute this A union with B, then I distribute this A union with what? With D, such that I get, so when I distribute A union, B is this part, and of course I have intersection in between. Then I distribute A with union D, then I get this part. So that is called the distributive law. Distributive law, remember that one. Okay, next, what do we get? So we have this result where we're saying I have A A union theta, which is not theta, I mean empty set. So A union, we said the empty set would denote it like this, or would denote it by what? By parenthesis. That have nothing there. So now, what are we saying now? So we're saying A union. So A union, the empty set is just A. So if I have this set, I have the set A which contains something, then I bring together with something that has nothing. It hasn't changed anything. So it means that I'm going to have what? Set A. I'll still have that set what? That set A. Then when I look at now, A intersect what? The empty set. A intersect the empty set. So I have A here. A contains something. Remember, let's say it contains 1. The empty set here, like this one, it contains nothing. So what do they have in common? They have nothing in common. So meaning that the intersection is what? Is empty. So the intersection is going to be empty. And this is what this result is telling you. You see, I have an empty set, I have a set A, they do not have any common element. It means that what? Their intersection is empty. The next one is A union, the universal set gives me the universal set. So if I have A, like this one here, the one which we drew here, this part. So we said A, this is A and the universal set. Now I'm bringing union, you're bringing all elements together. So it just means that I'll have what? All this here is going to be my union. But you see that all these that I've shaded is just the universal set. And thus you have the outcome that, oh, when you have A union, the universal set, you just have the universal set. The next outcome, or the next thing that we're saying is, when you're saying A intersect the universal set, it's just A. So the universal set is there. Let me draw this again. Let me erase here. So, okay. So we have this here. Then you have, okay, we have here, there, the universal what? The universal set. Then of course now the universal set, what? Then the universal set contains the set A. Then we're saying A intersect that set. So what is the intersection? This same part is common in what? In both. Because if I say E contains is the universal set, which is the set of all possible outcomes, contains 1, 2, 3. Then the set A just contains the set what? 1. Then intersect here. When I intersect, what do I just get? I get the intersection is going to be what? To be 1. Because the elements that is common in A and the universal set is 1. But 1, just that is the set what? The set A. And thus we just have this result to say, oh, we're just going to be getting the set what? The set A. The next result that we have is A union, A complement, A union, A complement. Okay, so what does that mean? So let me draw it here. So what does that mean? So if I have the set A, so I draw here, universal set, then like that, A. So the set A is this one. The complement is what is outside. The complement is outside. I think we talked of this one. Uh, so no, I think on the first one we were talking of intersection, but now this one here is the universal set, and that is the set A. Then we're saying the union, meaning I'm bringing everything together. If I bring everything together, I just have what? The universal set, and that's A union. A complement is the universal set. Intersection will just mean that okay, somebody's writing on my screen. I'm going to have I'm just going to have that to be what? To be empty. Okay, let me like this. All right. So now, as we said, okay, that did not go away. Uh, let me just erase this. Okay, where is my eraser? Okay, so it's here. All right. Okay. All right. So now let us continue from where we ended. If there's any question, you're free to ask. Then we're saying now A complement, A complement. So I have A complement, complement. This is just going to give me what? Give me A complement, A what? Complement. So the complement of the complement is just what? Is just A. So okay. Mm, let me demonstrate again on a Venn diagram here. So uh, we have, so if we have the inversor set again, E, like that, we have A. So A complement, we're saying, is everything here that is in the what, in the inversor set. Then what's the complement again of that? So the complement of that that are not contained, so elements that are not contained in here, then meaning they have to be contained in what? In here. So meaning A complement is just going to give us what? The set A. Gives us the set A back. Then the other result, a very vital result that we are seeing next is this one. When we have I mean E complement, the inversor set complement is just empty. So if E is the set that we are looking at, the inversor set is the set of all possible outcomes. Here is where they have to sit. All sets have to sit in here. Everything has to sit in here. All elements, everything has to sit in here. If I take the complement of this, then I have nothing, because this is the only one cis I'm looking at. I can't go outside. There's nothing. So I'll have what? Nothing. So it's going to be empty. So in short, I'll have an empty set. Then the empty set now, complement of the empty set is going to be what? The universal set. If it's not in the empty set, it's probably in the what? Universal set is what this one is telling you next. Then the last here, just the De Morgan's laws, which will prove later on. So looking at the De Morgan's laws, the De Morgan's law just state that if I have something like U, so if I have U, I mean, if I have A union B complement, this is equal to A complement intersect B complement. So here you see that when I distribute my complement, so this is here, let me write it here. So what that means is this. So if I have A union B complement, the De Morgan's laws, that means if I'm going to distribute here, my my complement comes there, and it comes to my B, this sign is going to change from union to intersection, like this is what the De Morgan's laws are saying. If I start with A union, I mean intersect B, then I'm taking the complement. This here is just going to be complement there. I get A, then the sign changes to what? To B complement, and then complement there. So this is what we call the De Morgan's laws. Okay, now the proofs, we'll look at them in a separate class. For now, let us see if we can apply what we've just learned to an example, to an example. For example, here we have saying the set let A, so saying let X and Y be subsets of the universal set is the universal set. Simplify the following. So how do we simplify? A union B, then have what? Here have Y intersect X. So how do I simplify this? So if I want, I can go the route where, so what is A intersect B? So I have to visualize this. I can visualize this actually like this. So they're saying Y and what and X, and the universal set is here. So the intersection is here. That's the intersection. The intersection is what? Is here in between. That's the intersection. Then what is the, now they're saying that intersection, let us unite it with what they said, X. It means that the everything that is there on the intersection and the set X must come together. So this here must come together. It must be this. But this, as I am looking, this is just my set X. So this simplifies towards to X. So I can write this just simply as what? As X. It simplifies to X. Or if you even if you go the way where you start distributing here. So remember, we can use distribution. So that would be A union X. Then I have what intersect, then I have A what? I mean X intersect, I mean X union X. But remember what we said, X union X is, it's going to be X. And you see this here, you have intersection. Then you have what? X union Y. But then you look at the diagram again, like this. Union A union B is this. But what does it intersect with what? With the set X. So if you have the set Y here, X, saying like this, then this is A, X union Y. Then where is the intersection with the set what? With the set X. So you shade the set X and see where do these lines crisscross. They crisscross at the set X. So that is your what? That is your simplification. Next, quickly before this video cuts, is the other part. And the other part is just telling us A intersect Y, then I have A, union, then I have X intersect Y complement. So what does this mean? In fact, so what is X intersect Y complement? So if I have this uh, like this, then I have my set X here. Let me say X is there. Y. Y complement is everything that is not in the set what? In the set Y. Then I'll write it like this. It's not going to shade in Y, but like that. Yeah. So this here is Y complement. But this Y complement is intersecting with what? With with X. So X is here. So you see where those are going to crisscross. So actually you see they'll crisscross at a point, the set X here, uh, like this. Not the part where there's like an intersection. This part is what remains. This is what a picture of this. But what is this again? This is X intersect. The intersection part is what is this middle part now. So that middle part and what we got, meaning it will just cover up here, that part, because we're saying union, you bring those things together. And this also just leaves us with the set what? You just have this OK is going to be the set X again. Look at it to be that, the set X. Or you could go the way where we say you have something in common. So mean it was distributed. You can factor out Xn, X intersect